Hello everyone, I am Kumar and welcome to Introduction to 5G. So 5G has been introduced within the release 15 version of 3GPP specifications, whereas 4G was introduced within release 8. Now 5G has been specified based upon the requirements of the following use cases. So the number one is enhanced mobile broadband, which is also in short we call EMBB. So enhanced mobile broadband addresses similar market to LTE but with improved capabilities. In particular, the EMBB use case calls for a higher data rate rather than LTE can provide. In terms of the peak data rate in ideal conditions, the expected data rate in more typical conditions, and the minimum in conditions of poor network coverage. The second one is ultra reliable and low latency communications, that is URLLC. So ultra reliable low latency communications, also known as critical communication, is a use case characterized by the need for very low latency, often in conjunction with very high reliability. Now coming to massive machine type communications. So the massive machine type communications, also known as Internet of Things IoT. So these terms both refer to wireless communications between autonomous machine type devices without any direct human interaction. However, the first term is sometimes restricted to point-to-point communications, whereas the second always implies that the device communicate over the internet. Now, the radio access network belonging to 4G is known as long-term evaluation, whereas the RAN belonging to 5G is known as new radio. So NR has been standardized to allow tight interworking with LTE. Tight interworking supports the interconnection of LTE and NR base stations. These base stations can then be used in combination to serve the population of user equipment. 5G network architecture based upon tight interworking between LTE and NR are known as non-standalone. So we will discuss this non-standalone in detail in the later part of the slide. Now the next point is standalone NR-based stations which provide connectivity to a 5G core network. The combination of NR base station and 5G core network is known as a 5G system. The benefit of 5G are maximized when using a 5G system. Now let's talk about technologies for 5G. So the very first one is network function virtualization, which is also known as NFV in short. So this is a recent approach in which the network elements are implemented using software in the form of virtualized network function VNFs. These functions then run on general purpose commercial off-the-shelf hardware, that is COTS hardware. So earlier it used to be proprietary hardware used by different MNOs, but now with the use of NFV, COTS hardware can be used for these functions. Now the next point is software-defined networking. So at the highest level, each element in a traditional communication network handles two main tasks. Functions in the user plane, forwarding traffic from one network element to another, for example by using routing tables, while those in control plane carry out higher level tasks such as configuring the routing table and managing the network's resources. Once again, that approach is perfectly satisfactory but has several limitations. The decision-making process are distributed over entire network, which makes the control plane unnecessarily complex, while those complexities limit how far the operator can distribute the function in the user plane. So the central feature of software-defined networking is a clear separation between the control plane and user plane. So in a software-defined network, the control plane functions can be centralized, which allows for simpler, more integrated control over the network. Once centralized, those functions can easily communicate with authorized third-party application server over a so-called northbound application programming interface, through which those servers can influence or control the network's operation. The third-party servers do not know any detail of the network's physical implementation, as those are confined to the southbound API, through which the control plane functions configure the ones in the user plane. In turn, the user plane functions can be distributed to whichever physical locations are desired, without the constraints that the control plane previously imposed. So that NFV and SDN, that is the network function virtualization and software defined networks, are complementary technologies. The first separates the hardware and software in the communication network, while the second separates its control and user planes. Once again, 5G has designed with SDN in mind from the beginning. Now coming to network slicing. So NFV and SDN provide a network operator with a flexible underlying resource which is easily reconfigured to handle changes in network traffic. Taking those concepts further, network slices are virtual logic subnetworks which run on shared underlying physical hardware and which are realized by means of NFV and SDN. A network operator can set up, reconfigure, and tear down individual slices as the need of them arises. Each network slice is optimized for the traffic that it carries. For example, a network operator might use different slices for each of the main 5G use cases, with the enhanced mobile broadband MMTC and URLLC slices respectively optimized for a high data rate, a high connection density, and low latency and high reliability. An operator might also use different slices to subdivide those use cases. For example, the EMBP use case might be realized using different slices for internet traffic, IMS voice and video, and public safety. Different slices might also be used for an operator individual customers, such as mobile virtual network operator that do not own any infrastructure of their own or industrial clients. Now coming to technologies for air interface. The 5G air interface uses two important technologies. Firstly, 5G can operate over a wider range of radio frequencies than previous systems have done, up to a maximum of about 50 GHz. At the highest frequencies, the radio waves have a wavelength of millimeters or tens of millimeters, so they are often known as millimeter waves. While using millimeter waves, the 5G air interface can occupy a far wider bandwidth than it does at lower radio frequencies, so its capacity can be far greater. However, the use of millimeter waves also leads to a number of coverage related issues, which we can discuss in some other topics in detail. Secondly, 5G makes greater use of multiple antennas than previous systems have done, typically using just a few antennas at the mobile, but using tens or even a few hundred at the base station. It applies them into two distinct ways to improve the coverage of the air interface at high radio frequencies by means of beamforming, and to improve its capacity at low radio frequencies by means of multi-input, multi-output MIMO antennas. Now coming to high-level architecture of 5G. So architecturally, 5G builds on LTE by adding a number of new components that are shown above in the figure. The 5G core network contain new network functions that support NFV, SDN, and network slicing. All those 3 points we have discussed earlier in the slides. The next generation radio access network (NGRAN) introduces new interfaces and signaling procedures for the backhaul and for communication between nearby base stations, and supports RAN centralization and virtualization, edge computing, and network slicing. Together, the two networks form the 5G system. The 5G base station is known as a next generation Node B (GNB). The GNB communicates with the mobile over an air interface known as New Radio, which supports millimeter wave and multiple antenna communications. Now coming to architectural options. So here we will discuss the various architectural options possible in 5G. So here you can see up to 7 different options which is viable for 5G deployment. So option 1 is a legacy LTE system that supports dual connectivity. Option 3 replaces the secondary eNode B with a secondary GNB and is the one most commonly used by early rollouts of 5G. The next two options introduce the 5G core network and the next generation RAN using a master eNode B and an optional secondary eNode B in option 5 and a secondary GNB in option 7. Each of these options is a non-standalone implementation of 5G because the GNB can only operate in conjunction with a master eNode B and cannot operate alone. In the last two options, the GNB takes on the role of the master, operating either alone or with a secondary GNB in option 2 and with a secondary eNode B in option 4. These options are known as standalone implementation of 5G. A standalone operation is only supported using the 5G core network, not when using the evolved packet core. So these are the 7 architectural options possible for 5G deployments. So guys, that's the end of our introduction to 5G. In the next part of this series, we will discuss about the air interface and the various aspects of functionalities of core and RAN functions. Thank you very much, guys.